now it's time to start talking about the transformations of tangent and cotangent functions. And you can see in this image right here, it's not the best quality, I'm sorry about that, but we have a bunch of key points and features that we want to talk about. And we have a bunch of vertical scalings, equations of midlines, and so on. We'll go through that. But most importantly, this is not your plain old vanilla parent function. This thing has been stretched around, moved, all sorts of stuff is happening. Now, let's go through the key points and features first on the right. I just want to make sure we understand how to find those. When it asks for something like what's A, what's B, C, and so on, all it's asking for is an equation or coordinate to describe that point. So A, for example, that's this asymptote on the left side. And I know it's hard to see, but that is a pi over 16 right over here that I'm looking at. That's the x-coordinate. So we would say x equals pi over 16. That is the equation of a vertical line. And likewise, this point E over here, that would be x equals 9 pi over 16. It's very important to note your asymptotes. They're helpful when you try to calculate the equation of a tangent function. Now these points, you can usually just go onto the graph and read them without too much effort. That's going to be 3 pi over 16 in x, and looks like negative 7 in y. We've got a 5 pi over 16 and a negative 4 for point C, and it looks like a 7 pi over 16 and a negative 1 for point D right here. Okay, those were those three central points of the function. Now, let's talk about what these mean in terms of the vertical scaling, equation of midline, and so on. So if you remember what midline is, I think that's a good place to start. Midline is the line that runs through the dead center of your trig function. And we can see it right here at negative 4. So we would say y equals negative 4 from looking at the graph. And the amplitude lines, the vertical scaling lines, really, we think of them as amplitude from sine and cosines, but with tangent and cotangent, it's vertical scaling. Those are right here, these upper and lower bounds of this graphing window that I'm looking at. And the question is, how much did you go up or down to get to those lines? And the factor you're going by is 3, right? From negative 4 up to negative 1 or down to negative 7. So we would say the vertical scaling factor is 3. Okay, now what's next? Period. Great. So the way I calculate period is I'm going to look at this graph and say, hey, I've got two asymptotes right here. And the function goes through one complete cycle within those two asymptotes. So that defines our period. It's the distance between these guys. How far is it from pi over 16 to 9 pi over 16? Well, if you're quick with math, you might say, oh, it's 8 pi over 16 distance. But the way we do that is we would say the end point, 9 pi over 16, minus the beginning point, which is pi over 16, which gives you, 9 minus 1 is going to be 8 pi over 16 on the top. And if we simplify that, we just get pi over 2. So our period for this particular tangent function is pi over 2. And if you remember your parent tangent function, you'll know that's different, right? The parent function was pi. Now it's pi over 2. So something has changed in this equation to make the period shorter. And the b factor is what's responsible for that. This next one I'm talking about, the b value. So if you remember your equation for period, that is pi over b. Now, we know that the period, from what I just talked about, is pi over 2. So what does b have to be in order to satisfy this equation? You can either look at it and say, oh, I see, b equals 2. Or we can go ahead and solve this, right? Multiply each side by 2. And then multiply each side by b. And then divide each side by pi. Or cross those pi's out. You get b equals 2. Okay, so that's the b factor right there. And that will be useful when we're building our equation for this function. The phase shift. If you think about where the phase shift is on a tangent graph, this is the easiest way I have for it. The phase shift is just dead center, right? But it's vertical. The midline was horizontal. Phase shift runs vertically. So what's that value? It's 5 pi over 16. And it's always going to be in the center for tangents. Cotangents is a little different. We'll get into that in a bit. So now I'm ready to write the tangent function. And if you remember the standard form, it goes like this. You have your vertical scaling factor times the tangent of some horizontal scaling b times x minus the phase shift h plus the midline k. So if we put everything together, now we're going to have 3 times tangent of b is 2, x minus phase shift is 5 pi over 16, and then k is negative 4. So this is our tangent function. Okay, and that's the way you build these things. Now, this problem doesn't show it in my screenshot. I didn't have room on my screen for it, but the next part of the problem says, what is the cotangent function? Okay, cotangent function is basically, if we look at this graph and pretends that the equation that made it was a cotangent equation, what would that be? And the way you do this is you have to remember what the shape of a cotangent function is. Okay, let me get some room here. The shape of a tangent function is this, right? Unless it's been transformed to a negative tangent function. But the shape of a cotangent function is this, right? It starts high and it goes down like this. So we can see that we're kind of flipped upside down from that. So at the very beginning, I know that my tangent function compared to my cotangent function has to have a negative sign in the amplitude or the vertical scaling. So whereas this other tangent function had a 3 tangent up front, I know that my cotangent function is going to start with, see, I left out my vertical scaling. It's going to start with a negative 3 cotangent. It has to be a negative scaling compared to the tangent function because cotangent functions want to look like this. Okay, but it's flipped upside down. So it's going to be negative 3 cotangent. Now b hasn't changed. So we still keep b in there. We still keep x in there. The phase shift will change, but the midline won't. So almost everything about this equation does not change when you write it as a cotangent. You can use all of that work you put in. All that changes is the sign of the amplitude right there and the phase shift. Those are the two big things you got to watch out for. Now, where does a cotangent function start? Well, unlike tangent, which starts in the middle, cotangents start at the left asymptote. Okay, or really any asymptote would be a fine starting point because these functions repeat themselves forever. But we'll use the left starting point, and I'm going to say that phase shift, according to this graph right here, is pi over 16. So I would write it this way, pi over 16. This is my equivalent cotangent function, and I'm just going to put that tangent function back up here so you can compare the two of them. You see, hardly anything changed. It's just the sign of the scaling factor up front and the phase shift. And it really is as easy as that, switching between tangent and cotangent functions. Both of these equations describe that graph that I'm looking at up here.